Hi folks, we're going to take a look at number 17 from page 129. So they give us the velocity function for an object, and they tell us that b and g are constants. Now this is a little different because normally, and of course, velocity is a function of time, but we see that the variable inside the equation is not actually time. So it's a function of the position function, which also is a function of time. Okay, so while we don't see the variable t in this equation, we're assuming that if we're talking about velocity and position, these are functions of time. Okay, and what they want us to do is they want us to show that the acceleration is constant. Now, of course, the acceleration is just the derivative of the velocity with respect to time. So this is what we're going to be finding. Okay, where we're looking for the derivative of the velocity with respect to time. So that means we have to take the derivative of this function here with respect to time. Okay, now just to make things a little simpler, I'm going to rewrite this with the square root being replaced by the exponent of 1/2, just so that the chain rule will be a little clearer. So b squared plus 2gs all to the 1/2. All right, so we're taking the derivative of this function here, but it's a composite function, so I have to use a chain rule. So start with the outside function, which is the x to the 1/2. So make this my u. So first I take the derivative of u to the 1/2 with respect to u. So that's just 1/2 u, which is b squared plus 2gs all to the negative 1/2. And then I have to multiply that by the derivative of u with respect to t. All right, so let's see what happens here. Well, b squared, remember b was just a constant. So the derivative of b squared is just 0. All right, this is where we have to be a little careful because, first of all, 2g is just a constant. So if I'm taking the derivative of 2gs, it's just going to be the constant 2g times the derivative of s with respect to t. Okay, now I don't have the function for s that I can take the derivative of, but this is where I realize, hey, wait a minute, what is ds dt? This is just the derivative of the position function, which is just equal to the velocity function. So this part of my expression can just be replaced with the velocity function. All right, and we're going to see this is all going to work out nicely. So here, let's do some simplifying. This 2 and this 2 are going to reduce. All right, so this has a negative exponent, so I'm going to bring it to the denominator. So what do I have in the numerator? I've got g. Okay, and I've got the derivative of s with respect to t, which we realize is just the velocity function. So I can replace that by square root of b squared plus 2gs and all of that. Remember, this was going into the denominator because of the negative exponent. So that's just going to be the square root of b squared plus 2gs. And hey, look what happens. The two expressions that contain the variable just reduce. And what am I left with? I'm just left with g, which of course is a constant. Okay, so what have we just shown? We've just shown that the acceleration, which is the derivative of the velocity, is a constant. All right, so let's recap here. First thing was to, not get thrown off by the fact that v was given as a function of the position function. Okay, but we also have to remember that these two functions, s and v, are just functions of time. Okay, so when I'm finding the acceleration, I'm finding the derivative of velocity with respect to time. Okay, and the way in which we did that was to carefully apply the chain rule correctly. All right, that's it for this one.